When we say I see, we usually mean I understand. Let's look at how the human eye interacts with light to help create a visual understanding of the world around us with PASCO's human eye model. PASCO's human eye model helps shed light on how the parts of the eye work together to make vision possible. The model comes with two sets of 6 convergent and divergent lenses, 1 pupil aperture with human eye pupil shape and cat eye pupil shape, 1 retina screen, an optics caliper, 1 adjustable focal length lens with syringe, tubing, and 2 flexible lenses, and an instruction manual that includes background information and investigation ideas. You will need a bright, artificial light source illuminating an object or an asymmetrical drawing, or bright natural light coming from a window. You could also use a device that creates an illuminated asymmetrical design, such as PASCO's basic optics light source. Regardless of the light source and object you choose, it is best to work with a model in a darkened room. The eyeball contains a built-in corneal lens. This is the retina. The circle in the middle represents the fovea, and the hole represents the blind spot. I'm going to place the retina in the position marked normal for now. I'm using the PASCO basic optics light source to investigate an object placed near the eye. Notice the dark arrow on the light source points down, and the bright arrow points to the left. When I point the eye towards the light source, you can see that light falls on the fovea. But it's blurry because the eye model has not worked to focus the image yet. And I can manually change the distance to the object to improve the focus. But let's see how the eye's adjustable lens solves this focus problem. In the process of accommodation, the ciliary muscles in the human eye change the shape of the lens to change its focal length, and this is how objects of various distances come into focus. Let's model accommodation by changing the shape of the adjustable lens model. The lens is placed in a septum slot behind the cornea. You can see the effect lens shape has on image focus. When you use the syringe to add or remove water to the adjustable crystalline lens, you change its curvature, and this alters the focal point, or the focal distance of the eye. Now that the image is in focus, you can see that it is upside down and backwards, which is actually what happens in your eye. This happens because light rays bend as they pass through the curved cornea and converge on the retina. This forms the image. Your brain combines signals from the optic nerve and positional feedback signals from your vestibular system to reinterpret the image the right way up. Now I'm going to pour about 1 liter of water into the eye. The fluid right behind the cornea represents the aqueous humor, and the larger quantity of water represents the vitreous humor. I'll remove the adjustable lens and replace it with a 62mm lens. If you don't have an optics light source, you can use a well-illuminated asymmetrical drawing. I'm going to add a little bit more light with this flashlight and adjust the distance to get the best focus. Let's investigate nearsightedness and farsightedness. The retina can be moved from the normal position to the near or far position to simulate a nearsighted eye or farsighted eye. A nearsighted person has an eyeball that is too long, causing the image of distant objects to be formed in front of the retina. You can select a divergent lens to place in front of the cornea and form a virtual image of a distant object closer to the eye. This is what glasses do. A far-sighted person has an eyeball that is too short, making the distance from the lens system to the retina too small. This causes the image of near objects to be formed behind the retina. Farsightedness can be corrected using eyeglasses that have a convergent lens. These are just a few discoveries students can make about how the human eye works when using the human eye model.